right, and welcome to Algorithms Live. This week, what we'll be covering is this binary lifting technique. Last week, during on Monday, on our Monday episode, we covered this problem ski resort, and I kept mentioning these things called LCAs when I was solving the problem, and many people didn't know what I was talking about. So this episode, what we'll be doing is I'll be going more in depth on how to find LCAs. And one such technique for doing that is this binary lifting technique. And I'll be doing two problems here. First one will be tourists, and I'll live code that one so you get to see how to implement this very cleanly. And then there's another problem that I don't really have a problem spec for, but it kind of just illustrates how flexible this technique is. And so we'll be looking for bottleneck paths in a graph, and that will be the second part of the episode. And I'll just be discussing that conceptually, and you can go code it on your own. There's also a nice code forces problem that you can try after the episode on your own. It's a few more observations than just the binary lifting by itself. But I'm confident if you understand how binary lifting works, you can go solve that as well. This is kind of a special episode for us too. This is the first episode where we've had 1,000 subscribers on the channel. So it's a big milestone, I guess. So thank you all for subscribing and viewing and keeping up with the show each week. So thanks to everyone. All right, and then I guess the last housekeeping item before we begin is just next week's episode will be on a Wednesday. I'll be going to Top Coder Open's regional event here in the US. It's in Austin, Texas this year. So before I leave on that, I'm going to be doing an earlier episode next week. That way it doesn't conflict with the traveling that I'll be doing. But if any of you are going out to that event, I'd love to say hi. So yeah, if any Austin coders are going to the TCO event that watch the show, that'd be great. If not, see you guys on Wednesday and then the subsequent episodes of Algorithms Live. All right, so let's get started. And the real motivation here for this technique that we want to be using is solving this problem of, hit that weird, least common ancestor. This is also called LCA for short. Really, it's just a piece of a graph. So what you're given some kind of rooted tree. It doesn't have to be a binary tree, so I'll add a few more nodes here. So we can just root the tree arbitrarily, or we just have some kind of a rooted tree. Maybe I'll draw out a bigger one. And what we'd like to do is we'd like to just select two nodes arbitrarily in this tree and find what their lowest common ancestor is, or least common ancestor. You can use those interchangeably. And so everything has the root as a common ancestor if it's a connected tree. In a forest, there may be no ancestor at all. But in a rooted connected tree, the root's always going to be an ancestor. You can view all the ancestors. And we just want the one that's furthest down the tree that's common to both these nodes. So an ancestor is just a node that you can reach by following your parents up the tree to get to a position. All right, so the first thing I want to do before we figure out how to solve this fast, we're just going to solve it naively. And so here's how I'm going to attack this. I'm going to store depth information for each level of the tree. So depth 1, depth 2, depth 3, depth 4. And you can look, these are all the nodes of depth 1, these are all the nodes of depth 3, stuff like that. What you're going to realize here is some of the nodes are at different depths. So let's say I'm trying to walk up the tree. I have something like some node I, some node j. What may happen is they might be at different levels in the tree. So we have I and j and so on. And then their least common ancestor, LCA, might be up here. You can follow paths up to the tree. So what I'm going to do first to make my life a little bit easier is I'm just going to walk up the tree for whatever that deeper node is, and I'm just going to move to make these two depths even. Right, so I'm just going to make these two depths equal by walking up the tree until their depths are equal. So I just take the deeper node and I just keep walking edge by edge, going up for the parent pointer. And then I can walk one by one. So for every single edge, I'm just going to take a step up on the left, take a step up on the right, take a step up on the left, until they end up hitting the same node. And that'll find my lowest common ancestor. So it's a two-step technique. The first step is just move up. And I'll use depth notation here, di minus dj steps. And you just move the deeper one up that much. And then after that, you just go one at a time, stepping in unison in pairs, and then you eventually, the two nodes will be equal and you found your LCA. The problem is this tree could be really deep, and so the runtime is not that good. You could have something that's O of n in depth, and if we're just doing this march up the tree one at a time, finding LCA could be O of n. So that's where we start with this idea of binary lifting. Okay, so here's the basic idea. We have some node here. And what I'm going to do is I'm going to say, well, maybe I could jump up the tree, which 2 to the 0 is 1. Or maybe I could jump 2 to the 1 up the tree. So that comes out as 2. Or maybe I could jump the way up a little bit further, 2 to the 2 up the tree. And so that's 4. Or maybe I could jump and then you could go really far up and just generalize it 2 to the k up the tree. Well, this is going to grow extremely quickly, so I really don't need that many power of 2 jumps. So the idea here is to build something very similar to a skip list. We're just going to store skipping at powers of 2 through our table, and it's really just the parent path up the tree that we're saving this skip list information. So here's how the table looks. We're just going to make the table a 2-dimensional array. And so what we'll do is we want to store something like 2 to the k is the path length. Well, we'll do that by keeping track of k, because the 2 is constant in all our jumps. And then I'll say I, well, that's node I. So it's just a little 2D table here. You'll also notice that table of 0 of I is basically the same as if I had a parent pointer on my tree. So it's the parent of I, because that's just 2 to the 0 is 1 up the tree. So it just jumps that far. So let's figure out the size of this table, like how many Ks could end up happening here. Well, what we're looking for is when does 2 to the k end up equaling n? Because it always has to be less than or equal to n. We don't have to store any k bigger than that because we jump off the tree. So we just rework this with a little bit of algebra. And we show that you don't need more than log base 2 of n for your k. So we can compute some things with log base 2 of n. And so our table, our 2D table, since there are n nodes, and then I have these log n different k values that can exist, our 2D table is going to be no bigger than n times log base 2 of n in size. Or that roughly gives us the size of the table. So it's a little bit extra memory than some of our other data structures that are order n in size. But that's okay. We can be a little bit wasteful in memory here. we're basically getting it back in convenience. Okay, so let's talk about how you build this thing. So the first thing you do is you just store parent pointers. Using the table 0, you're just going to store what's my parent in every position in the tree. And then what we can do is kind of do this inductively. Let's say I've computed all jumps of size 2 to the k for some k. What I could do is I could make 2 jumps of size 2 to the k up my tree. And what I'm left with, if I make 2 jumps of size 2 to the k, it's 2 to the k plus a jump of size 2 to the k, which is 2 times 2 to the k, which is 2 to the k plus 1. In other words, this jump is equivalent to 2 to the k plus 1. So all I do is I use what I've already computed before to compute the next level for 2 to the k plus 1. So I use the table of k with all those I values to build table of k plus 1. Now you can do this build 1 by 1 by 1. So just iterating over k's. You can also do this build in a different order. So if you were trying to solve ski resort from last week, one of the things you can do is you can be building your tree down like this. And then as you add a new node, what you can do is just do update 2 to the 0, update 2 to the 1, update 2 to the 2, update 2 to the 3, all the way up to the max value you need. And so in log_n time, you can add a new child to your tree and update the skip list that way. And it's a little bit different order. So sometimes you can build this table all at the beginning by looping over all k values, then over all I values. Or sometimes what you want to do is you want to build the tree dynamically, and then in log_n time, update for a new node all these power of 2 jumps. Both work perfectly fine. Okay. So that's what the table looks like. So let's write a handy little helper function here. So our first helper function is going to be called walk. And it's going to take in 2 parameters, I and k. So here's the idea with this. I is what node I'm currently on. K is the size of the jump that I want to go up the tree. So very quickly, what I want to be able to do is jump up my tree k edges just as quickly as I can. Well, one thing I notice is I can take this number and represent k in binary in base 2. So another way you could be thinking about this binary number is just 2 to the 5 plus 2 to the 2 plus 2 to the 0. So I basically have 2 to the 0 in this position, 2 to the 2 in this position, and 2 to the 5 in this position. So if I was writing it out in binary, it maybe would look something like this, plus that. And you add those together, you get this k value. So what I can do in terms of my jumping is I can be at some position I. If I want to jump up to this binary number, well, I could make a 2 to the 5 jump, followed by a 2 to the 2 jump, followed by a 2 to the 0 jump. And I can do that fairly easily. Let's start off at I. I could go from I can compute my next I by going from table 5 I. And the next iteration, I could go up to table 2 of I. So I've jumped up my tree. And then the last step, I just jump up by 1, which is table 0 of I. And so I'm just walking up the tree very quickly. They're at most log_n bits in a number, so that's at most log_n jumps up this tree. Pretty simple. All right, so that's the first helper function in terms of what you can do with binary lifting. Let's take a look at another. Let's show how we can speed up LCA computation. So I want a function for LCA. Takes in 2 parameters, I and j. These are nodes. And what I want to do is I want to compute the least common ancestor or lowest common ancestor of these two nodes in the tree. So step one is I'm going to use my walk function here, and I'm just going to walk I and j to be in the same level. So if I is deeper than j in the tree, I walk j up to be the same level. Otherwise, I walk I walk I up to be the same level. Otherwise, I walk j up to be the same level. All right. And then now they're at the same level, my strategy is actually going to be to binary search for the LCA. I'm going to talk about how to do this. I'm actually not going to code a raw binary search. I'm going to use the LCA table, how it's conveniently organized to do my binary search. So let's take a look at kind of what will happen in terms of my binary search. Say I have some I and I have some j. So what I'm doing now is I'm just assuming they're at this exact same level. And then I have some intermediate node that I want to compute to. So one consequence is I could make a really big jump in my table. So maybe it's a jump of size to the k. Maybe it's the max k value. What could happen is my search will go all the way up the tree, go through the LCA, and shoot all the way up here. And so there's this node that's maybe close to the root. And this whole path length is size 2 to the k. And then my j is at the exact same level. So what's going to happen is it's going to shoot through this node. They're going to meet here, but I overshot it with my huge size 2 to the k jump. And what you'll notice is when I'm too high on my search, these two positions are the same. So table k of I ends up equaling table k of j. And that's what happens in this case. So I've just shot way too far up. So that's the high case in my binary search. And this table lookup is of 1, so we're good there. So here's the other case. So here's I, here's j. I shoot up the table. And I hit 2 different nodes here. And they still have some path going up that reaches the LCA. So here's my LCA up here that I want to find. I make a size 2 to the k jump. And on this side, I make a size 2 to the k jump. And you'll notice that these are not equal. That's the big change here. So if I jump too far, the 2 table positions end up being equal. If I jump too short, the table positions are not equal. So what we're going to do is we'll just look at the way of thinking about this jump. So if I end up jumping too far, well, I'm not going to take that jump that's higher than the LCA. What I really want to do is jump just short of the LCA. So imagine here's my LCA again. Here's I, here's j. There's some path I could take and find the node just shy of getting to the LCA. And on this one, I could find the node just shy of getting to the LCA. Right? And whatever this length here is, maybe I call this k, this can be represented as a binary number. So what I'm going to be doing is I'm just going to be making really big jumps when I can. And if I take the biggest jump that doesn't push me past that number, I can actually walk down the binary representation of this number and find out exactly where these 2 nodes are. So let me give you an example here. Let's say my number is this in binary. Well, what I could do is I could make if I make a jump of 1, 0, 0, 0, 0, 0, 0, so in my table, this would be table 6 of I. This jump is way too far because it goes past the target number that I'm trying to get to. And so I don't need to know what this target number is. I just know that if I jump too far, the numbers will end up being equal. I'll find an ancestor in my tree. So then I try the next number, and they turn out to be okay. So what I'll do is I'll jump that far, and then I'll say I'll just jump that far up the tree, and then I'll just look for the remaining number with that number removed. So then I move to the next position, and I try jumping this far. Well, again, if I'm basically jumping to this far above my 2 nodes, and that's less than my target position, so I'm okay. But then I might try jumping to this position, which is much further. This is a bigger number than this one. So that goes much further than my target position, just shy of my LCA. So I know I'm not to take that jump. And I can continue on in this fashion. And I'm basically just trying to take power of 2 jumps that get me as close to the LCA as possible, but not actually hitting the LCA. So I'm just advancing to just short of the goal. And then once I get to those positions, I just go up 1 from that position, and that will be the LCA. So go from where I am to 1 above. All right, so this brings us to our problem that we're going to try to solve with this binary lifting technique. So this problem is on Caddis, and I posted it earlier today. It's called tourists. Okay, so the problem is very simply stated. And for anyone that's interested, Dion Nicholas is the writer of this problem. So he was on episode 1. This is one of his other problems that he wrote for this contest. So it's the problem is written as the sum of all paths in a tree such that I divides j. So these are pairs of locations in the tree, and I is less than j. So we want to find all pairs of vertex ID where I divides j and I is less than j, and then sum all those path lengths together. So let's take a look at what the sample tree looks like. Okay, so that's my sample tree. What I can do is I can just pick 2 nodes on this tree. And what I'd like to know is you can see that this is vertex 2 and this is vertex 6. So 2 divides 6. So that's a path I want to count. And the number of edges I use is exactly 5. So I'd be adding 5 to my count. So I'd like to know that path length very quickly if it's possible. So we've kind of got a problem here because there are n squared nodes in this tree. And in this problem, n is up to, I believe, let's see. I believe it's 2 times 10 to the 5th. Yeah, 2 times 10 to the 5th. So pretty big. This tree can get fairly large. And so if we try n squared nodes in this tree, this is going to be way too slow. So you might ask yourself, well, they're divisors. It's not really all pair. It's only all pair of one dividing the other. So you might say, well, how many ij pairs are there? All right, so let's write some code to find all ij pairs first. It'd be a good way to analyze just how many ij pairs that there are. So we're just going to pick all I values from 1 to n. So I'll just write a for loop. And then I'll write a second for loop, which is going to start by 2i, and then increment each time by I. So I'm basically starting at 2i, then going to 3i, 4i, 5i, 6i, so all multiples of I. And that will give me a pair ij. All right. So that's basically all multiples of I for every single I. Let's analyze this with a summation. So we get I equals 1 to n. And this innermost loop for every single I is going to run n divided by I iterations. Well, n is a constant with respect to the summation, so I can pull that out. And what I'll get here is I equals 1 to n of 1 over I. And what I like to do, or what I basically have here, is this right here, this sum right here is called a harmonic sum. And it's pretty well known that a harmonic sum is O of log n. Okay, so what this entire thing will come out to is n log n. And as a lot of you have already noticed in the chat, this loop right here, this pair loop right here, is a prime sieve loop. So it's very similar to the prime sieve. So if you saw that code before, you know that it's bounded by n log n in terms of runtime of generating these pairs. But this harmonic sum right here, what I want to do is I want to give you some intuition why this is bounded by log n. So this is basically a sum of, here's what the harmonic sum looks like. It's 1 plus 1/2 plus 1 over 3 plus 1 over 4. And I can just keep writing these. So it's like, why is this bounded by log n? So what I'm going to do is I'm going to overestimate here. So I'll take 1. I'll take 1/2. But instead of 1/3, I know 1/2 is bigger than 1/3. So I'm going to put that here. Then I'll take 1/4. And I happen to know 1/4 is bigger than 1/5. So I'll overestimate a little bit there. And I'll keep doing this. So what you're going to notice with this estimation, this sums to 1, this sums to 1, and this sums to 1. And so you'll realize that the number of items in my summation that I need to get my next 1 is doubling every single time I get a 1. And so you can see how this kind of estimates that it's log n, because the number of numbers that I need in my summation, because the summation is shrinking really quickly, is doubling every time a 1 comes out. So that's why that summation of I equals 1 over I is O of log n. So not much rigor there, but this is the way I think about it in my head when I try to argue to myself why this is true. Although I'm sure you can do that a tad more rigorously. All right, so that's the harmonic sum. So we happen to know, let's see what we know right now. There are roughly n log n ij pairs that we can query. And so what we need to do is we need to quickly find the path lengths. Because if we knew the path lengths, what we could do is we could sum those together for every single query fairly quickly. So let's take a look at what a rooted tree looks like here. So I'll just draw a little rooted tree. Just kind of argue about this. So let's say I have a few nodes on my rooted tree. So right here and maybe right here. I want to find, so what I'm basically doing here is I'm just rooting the tree arbitrarily. So I'm giving an undirected tree, but my first step is to root it somewhere. Because when I root the tree, I get access to LCA, and that's going to help me. So what I really want to do is find this path through the tree, its length, very quickly. Right? And this length is going to be, one thing you'll notice is the highest point of the march through this length is exactly the LCA. I also have stored depth information for all these trees. I know how deep this node is. The depth of this node can be easily computed from the root of this tree. And the depth of the second node here goes all the way to the root of the tree. So what you'll notice is I want that blue piece, and I could count these two red pieces. So I'll call this side right here d of I, and I'll call this side right here d of j. So if I do d of I plus d of j, I'm overcounting by exactly twice this piece. So what I'll do is I'll call this, let's say that this node is the LCA. So I'll call that K. K equals LCA of I and j. Now all I have to do is subtract out what remains. So I'm going to subtract out, and I'm overcounting twice, 2 times the depth of my LCA. And that's going to be the equation that gets me the blue piece, which is the length of the path that I end up having. And so now I have enough information to actually solve this problem, which is great. So I just compute this depth information once I have the tree, and then I can solve the problem. So what I'm going to do right now is I'm going to live code this one. And I forgot to extract my keyboard, so let me go get that real quick. And then I'll start the live coding. All right. All hooked up here. Okay, so let's get coding. So one thing I know is I want to root this tree, and I want to store parent information, but I'm not really sure what my parents are going to be. I'm given the tree. I'm given no guarantees on the order the things are given to me. So I'm just going to code first is I'm just going to code a BFS that's going to tell me the parent information. So fortunately, that requires me to make an adjacency list. I really like the tree definitions whenever you're given in a problem where they tell you some guarantee about the order of edges in the tree and it's already rooted. But that's not the case in this problem because it's an undirected tree given to you. So, oh well, a little bit extra work for us. All right, so I will make an adjacency list. That will be the first piece that I'll do. So I'll read in all the edges. As we already know, a tree has n-1 edges, so just have to read in n-1 of these. Okay. I can write my BFS. So I need to store some parent information, so might as well start writing my binary lifting table. And while I do this BFS, I'm also going to store the depth information because I need that to calculate how deep everything is in my tree. So I'll make my binary lifting table here as well. So the binary lifting table is an array of parents. And I'm going to have some max depth that I can go in my tree. So I'm just going to call that D. So I'm going to compute this value D. So that'll be interesting to have. Let's start off by making the binary lifting table. How big should D be? Well, D is the biggest jump that I can have, and N is the number of nodes in my graph. So what I'm going to do is I'm just going to say the largest jump I can make is size N, where it's really n minus 1, but I'm just going to give myself some padding room. So what I really need to do to compute this d, which is the largest k that's feasible as a power of 2, is I need to take the floor of the log of the number in base 2. So there's a really convenient way to do this in Java. So there's a function called integer.highest1bit. And what this will do is if I have some number in binary, so let's just take a look at a number in binary. I could have some number like this in binary. And highest 1 bit is just going to erase all the other bits that aren't 0. And that's what highest 1 bit's going to do. And if I want the floor of the logarithm, I just need to know how many zeros are after that number in binary. And luckily for me, integer has a function called number of trailing zeros. So it's kind of just a nice little 1-2 punch that I always do. So really what this is doing is the floor of log base 2 of my integer that I'm passing it. Just makes it easier to do the binary lifting for my table. So I'll do d plus 1 and n. I also need to store depth information, so I'll store it out to n. And what I'll do is initially say that everything in my table, maybe I'll just fill this with -1s. So basically, I'm just using -1 to signify I jumped too far up my tree, or that I don't have an edge currently for that power of 2. Okay, so let's go to BFS, for breadth first search. I need a scene array. I'm going to root the tree at 0. Seems to be convention. All right, and while I still have nodes, keep extracting nodes. Maybe I'll do it this way. If I haven't seen the node, then that's when I'll explore it. So if I haven't seen the node, now I go exploring. And when you do a BFS, I get a BFS tree. So I'm just going to hook up some parent information real quick. In terms of I'm exploring this edge down, so I get a parent coming up my tree. And then I need to increase my depth information for j. And so whatever the depth it was to get to node I, j is 1 plus that. All right, so that builds my tree. So now I need to construct the binary lifting table. So I have all the parent information. So for k equals 0, I'm good. So I need to look at all the other possible depth pieces. So instead of k, I'm going to use d for the exponent of power of 2. Let's use k. Being a tad indecisive today. It goes up to the max depth in the k value. Okay, so I'm just looping all those in order. So I have the previous value of k completely computed. And for k equals 0, it's already handled in my parent. So what I'm going to do is first, I'm just going to jump up by whatever k minus 1 is. So 2 to the k minus 1, I'm going to make that jump. And if I didn't jump off the table, then what I'll do is I'll make parent of d equal to the parent of k minus 1 of mid. I'm basically just doing 2 jumps. And then halfway through those 2 jumps, I make sure I didn't jump off the table. Makes it a little easier to code. Right. So that's my binary lifting table. So I need some extra information here. in terms of doing the functions I talked about for binary lifting. So I need two functions to solve this problem. The first one is my walk function. So what this will do is it'll walk up the tree exactly k steps. And here's how I'm going to code this. I'm just going to start off at the first exponent, and I'm going to walk through the binary number k. And I just have to make sure that I don't jump off my table, because I don't want to consider maybe that I've already jumped off my table. I just want to return -1 at that point. So I'm adding that in. So I just query my binary number and say, do you have the dth bit turned on? And if so, then I'm going to jump by that amount. So that's walking up the table. So I'm just really going back to the picture here. Let's go find walk. Yeah. What I'm doing is I'm just jumping up. What I'm really doing is I'm actually jumping up by the smallest bit first. So I'm doing this jump, then a size 2 to the 2 jump, then a size 2 to the 5 jump. So I'm doing once for every single bit that's turned on. So whenever I see a bit that's turned on, I jump that far. And that's how I'm handling that piece. OK. And so that's my walk function. Now I can compute LCA. So the first step in computing LCA is I check up on my depth information. I want to make these two depths equal. So if I is the deeper node, I needs to walk up the tree. There's also the case where J needs to walk up the tree. And so after I do that, I and J should be equal in depth. So we're good there. So if I is J, and then if I and J end up being the same node, so this handles the case where I is an ancestor of J or J is an ancestor of I, or they were both equal when it is passed to me, I just return 1, or I just return I. So the reason I'm doing this right here is I could have, remember, when I do my binary search up my binary lifting table, I'm looking for the node that is just shy of my LCA, right? So I have to stop just short of the LCA. So that's why I have to handle that piece as a special case. Okay. So let's run up the table. So I just try the largest jump I can first. And then if they're not equal, then that's when I take the jump. Notice that if I jump off the table with both of them, they're both going to be -1 and still going to be equal. So that also handles jumping off the table very elegantly. So if they're not equal, then I just take the jump. That's all I do there. And then I just return my immediate parent. And that's how I jump up the binary lifting table. OK, so I've computed that information. And the whole point of doing all of that is so I could write a nice convenient distance function for I and J. What I can do is return the depth of I plus the depth of J. Yes. IJ. So there was a comment in the live chat saying that first I was using K, and then I switched over to D. So I switched over to D to avoid this conflict of K. And then I ended up using D again because it matched the D that I was given. But in the notes, I had written it as a k value and not a d value. So let's just change that to be consistent. Yeah, just use the first instinct. And then I even called something d that was actually k. Oh, wow, I'm mixing variables everywhere. So I'll just get rid of all those k's. There's also a question is like, is the stream that we're doing on specific days? Usually this is the time for the live stream. But when we have special guests, sometimes the live stream is on a different day. And recently my schedule, I've been traveling and or I'll be traveling next week and things like that. So the day will change up. Last week I had the episode on Monday because I was avoiding CodeJam. I wanted to compete in CodeJam. So, and I'm sure a lot of you would be competing in CodeJam as well. So works out. I try to avoid timing these things during programming contests. Suppose that makes sense. All right, so the last thing we need to do is we need to loop over all possible answers that can exist. I'm going to use one base indexing here because that's the thing that will get me the multiples. So I can write out my, I'll do I plus I for j. Yeah. And actually, I was slightly wrong in the problem. So reading this real quick, they actually want the number of nodes crossed in the path, not number of edges. So I actually need to add one here in terms of my answer. And that should print my results. Okay, and that's pretty much all the code there is to it. Let's give this a test and make sure that I don't have any bugs. And it comes out to 55 for the sample, so that's the sample is correct. So let's try submitting to Caddis. That is not Algorithms Live. So that will be running for now. We'll see if I get this one. So as I have to refresh Caddis. It's looking pretty good though. Yes, accepted. And in 1 second. Not bad. Probably one of the faster Java solutions, I hope. Oh, and I just downloaded my code by accident. All right. Let's go back to the notes here. And what I'd like to do for the remainder of the episode is show you one more cool problem involving LCAs. So here's the problem. So you're just given a directed graph or an undirected graph. So given a graph, our goal is to find the bottleneck. So the max bottleneck from I to j. And so initially what we're going to do is we're not going from, so I'll write out I to j. I'm only just going to find one bottleneck. So I'll give you I and j. We have to find what's the path that maximizes the minimum edge taken along that path. So let's take I'm going to draw out a graph here. So maybe that's 8. Maybe this is 6. Something of a classic problem. Find the minimum bottleneck. There are several ways we can compute this. All right. So let's take a look at a few of these paths. Let's say I take this path, something like that. Then the minimum bottleneck on this path, the smallest edge I've taken is 2. But I can actually do a bit better here if I'm careful. I could make a path that went something like this, and then the minimum bottleneck edge I take is 3. So what I'd like to do, given a source and a sink, or a start node and an end node, I'd like to find what's that minimum bottleneck. Okay, so here's my first idea. One technique that can work quite well is to do a modified Dijkstra's. So I'll write that out here. Maybe shrink this a bit. So I use Dijkstra's shortest path algorithm, but instead of storing the length of the path for every single node, I'm just going to say the max number used, or maybe max edge used to reach I. And every time I try traversing an edge, I just, instead of adding the cost that it took to get to node I, plus the weight of the edge, what I'll do is I'll take the min of the cost it took to get to node I, and then do ij. And so if I run Dijkstra's in this fashion, and I use a priority queue where I'm maximizing the biggest thing I've taken so far, I'll explore all the largest edges first, and then it'll shrink down to smaller edges. So this is one possible solution for solving the bottleneck path problem. I just run that from one of my sources. There's another way we could do this, though. We could do a binary search on the min edge taken. So I could binary search on the min edge. So let's just do an example here. So I'll draw out my graph again. Maybe I'll try copy and pasting it. That would be exciting. So here's my graph. And what I'd like to do is I'd like to, let's say the max edge I'm going to take is 3. Because that's my answer. I want to see what the graph looks like. What I can do is I can just delete every edge that's less than 3. Oh, that was 4. But I can delete every edge that's less than 3 from my graph. And then what I'm left with is some graph. And then if I can reach from the source to the sink for a given path, then that was a good enough number. And if I can't reach it, so let's say I took 4, then this was too restrictive, and I couldn't reach from source to sink. So I could do a binary search on this value and then run a BFS seeing if I could reach it or not. So does the graph disconnect nodes? So that's solution 2, is the binary search. And the last one is kind of maybe a bit surprising. What I could do is I can construct the minimum spanning tree. Or in this case, a maximum spanning tree. So I'm going to construct a maximum spanning tree. So in terms of this problem, this was actually the maximum spanning tree. You could take the original graph, maybe scroll back in the video. You could run maximum spanning tree on this. You would actually get this tree. And then the unique path from one node to another, and it's any pair of nodes here. So if I take the path from here to here, for example, the bottleneck edge is always going to be this 4, regardless of what ends up being taken. So let's talk about why that is. There's this thing called the cut property. So there's many YouTube videos online or some reading you can do. You can look up the cut property of a spanning tree. So a cut is you take a bunch of nodes and you partition them into two sets. So you have all the nodes and the ones, and then there'll be some edges that cross the cut. Basically, the cut property ensures that in a maximum spanning tree, the heaviest edge is going to be the one that's in the spanning tree. And so, in other words, if you basically take the cut that maximizes this, the only thing you need to keep track of in terms of separating these two halves of the graph for any separation of the graph is that maximum edge that's taken. So it's sufficient to just keep the maximum spanning tree around if you're trying to find bottleneck edges. So what we'd like to do is find the smallest bottleneck edge from I to j. So we're going to make this problem a bit harder. We're going to make these queries now. So I'm going to try to find what's the minimum or maximum bottleneck possible. I guess, yeah, find max bottleneck. Yeah. Yeah. From I to j. That's maybe what I want to do. And so I'll have a bunch of queries now. So maybe 10 to the 5th queries of this form ij. And my number of nodes is up to 10 to the 6th. And my number of edges is up to 10 to the 6th. So now I need to do this pretty quickly. I want to find all these bottlenecks. So the Dijkstra solution is out. And the binary search solution is out. But having this minimum spanning tree around, constructing this very quickly, is going to speed some things up. So what I'll do first is I'm just going to construct the MST. That's my pre-computation. And the next thing I could do is I could root the MST. All right. So let's draw out this tree. Could draw out all kinds of crazy trees. It can be all manner of imbalanced. So 1, 4, 4, 5, 3, 2, 8. All right. So what we could be doing here is we could have two different nodes that are picked. And what I'd like to know is I'd like to know the path length from one to the other. I'd like to find this bottleneck edge. I could walk up my rooted tree and then walk down. So I'd like to know the lightest node on this path. It just happens to be this node here. Let's pick a different node that's not so convenient. It goes up here. It walks up to the LCA of these two nodes. This is the lightest node on my path. I want to point out one small thing, is inclusion exclusion does not work here. So if you look at this, going up and then going down, I can't just subtract something from here to get my answer out because I'm taking a minimum along this path. So I have to get around that somehow. I need to find this bottleneck path quickly in terms of anything else. Okay, so let's do something instead. I'm at node I. I jump up the tree 2 to the k in length. That's my parent node jump. So I'm storing some information on my parent of size k, jumping from node I. So it's a 2 to the I jump. What I could do is I could also store information on this path that's 2 to the k and jump. What's the min edge along that jump? So while I'm constructing my binary lifting table, I'm storing what's the parent along that jump, but I'm also storing what's the minimum edge I've taken jumping up size k. So in other words, if I do min edge of 0i, that's basically just the weight of the parent edge. So I'm at node I, this is the weight, this is min edge. And now when I construct my binary lifting table, I can also construct for a size 2k jump, I could construct two 2k jumps and end up getting 2k plus 1. And I could store for all powers of 2 jumps, what's the minimum edge along those powers of 2 jumps? All right. So when we want to find that bottleneck edge, we can be walking up to find our LCA and log in time. And as we're walking up the tree to find the LCA, we can also be storing what's the running minimum so far. So what we'll do is maybe I make a 2 to the 5th jump. And maybe I make a 2 squared jump. And maybe I make a 2 to the 0 jump. So jump, jump, jump. This form. And so this one is weight 1, this one is weight 2, this one is weight 3. So jumping up this thing. So what I can do is I can do the minimum of these 3 weights. And that will tell me the minimum along this whole path. So in log n time, we can find the bottleneck path just by using LCA finding, which I think is kind of cool. All right, so that does it for me tonight. This is basically how you solve this bottleneck pathfinding, both these bottleneck pathfinding problems. But if you want to use binary lifting, then that's a good way of handling it. Also, binary jumping on tree is another name for this. I'd go to the Algorithms Live blog, and you can check out the problem that I posted there, and it can give you some good practice with this technique, seeing if you're familiar with it, if you want to code a new problem from scratch. That one's a little bit more complicated than this one, but it's good to code something immediately after learning a new technique. And so once again, I'll remind you all that the next episode of Algorithms Live will be Wednesday, 9 p.m. Eastern Standard Time. So same time of day as this episode, except it's going to be in the middle of the week this time. So you can watch it live or you can watch it later. And I'll make another announcement on that later in the week. But thanks for watching, everyone. And I'll see you guys next week.